Hi there! Welcome to the third episode of the Digital Electronics Fundamentals series. After going through some basics in the previous episode, today we will look at a couple of more gates, and with that excuse, we will see how to use truth tables and some simple boolean algebra to design a logical circuit. You want to see how? Well, follow me through this whole video and you will master this useful skill. Let's begin!
Hi there! I am Carlo Carrano, and this is Electronics Engineering Made Easy.
The first gate I would like to talk about is the so-called XOR. Let's start with writing down the truth table, which will help us describe how this gate works. You can see how whenever the two inputs are different, the output is a 1. We could say that this kind of gate tells us if a number of digital signals are all the same or are different. The XOR port is available in integrated circuits that contain a number of them, like this one in the picture. And from the picture you can also read the full name of the gate, the exclusive OR. Another way to say that the circuit provides at its output an OR operation, but exclusively if the inputs are different. Like they say, if one or the other, but not both. Let's see now how we can draw the schematic of such a circuit starting from the truth table. There are two methods to use. The first one is to look at the rows that have a 1 at the output. We will look at the other method in a later episode. So, here are the two rows that have 1s on the output. Let's look now at the inputs. For each of these two rows, we write the name of the input as is if it is represented by a 1, and as a not input if it is represented by a 0. So, for the first of the two rows, we therefore write down not A and B. And yes, we consider this as an AND operation, so we write down the two inputs as if they were multiplied by each other. And now we are going to add to this expression the one for the other row that has an output of 1. Keep in mind that when we say add in Boolean algebra, we intend the OR operation. So, following the same rule we used for the first row, we then write A and not B. The result of this whole operation is our output, U. We have now a Boolean expression that can be easily translated to a schematic, if we just keep in mind what each of the symbols represent. Let's start by drawing the two inputs and the two wires on which we put them. Now, since we also need not A, let's add a NOT gate to the A. This way we can use the A or the not A depending on what wire we use. Since we also need the not B along with the B, we also add a NOT gate to the B input. And now let's draw an AND gate, which represents the first AND in the Boolean expression. The inputs of this gate needs to be not A and B, and so we draw the corresponding wires in the schematic. We will do the same with the second part of the Boolean expression, and so we will use another AND gate, which will have as its inputs A and not B. And finally, the plus symbol in the Boolean expression tells us that we have to apply an OR to the outputs of the two AND gates. And so we draw the OR gate, we connect to it the output of the first AND gate, and then we connect the output of the second AND gate also to the OR gate input. The output of the OR gate now is the output U of the Boolean expression. And this, therefore, is the schematic of the XOR gate, which is made with two AND gates, two NOT gates, and one OR gate. We can quickly double-check if this circuit works really as described by the truth table. Consider first the rows with an output of 1. In them, A and B are opposite. And now look at the circuit. Because in each AND we get both A and the opposite of B, we can be sure that we are inputting two identical values, either both zeros or both ones, on each of the two ports. And while we are inputting both zeros on one port, the other ports get both ones, and vice versa. The result is that one AND gate will have an output of 1, and the other AND gate will have an output of 0. And since these outputs go to the OR gate, the output of the OR gate will be a 1 in both cases. If we look now at the rows of the truth table where the output is 0, you'll see that the inputs are either both at 1 or both at 0. Back to the schematic, if A and B are both 1 or both 0, each of the AND gates will have at their inputs A1 and A0 because of the presence of the NOTs. And therefore the two AND gates will both have simultaneously an output of 0. And since these two zeros are the inputs of the OR, the output of the OR will be 0 in both cases. Description too complicated? Well, to make it simpler, let's use a simulator for digital circuits, and let's see in there how the circuit works. Here is the workbench of the simulator. I have already drawn the circuit with the 5 gates, and I also added a compacted version of the XOR gate. The two outputs are available at the same time, and the two inputs A and B are both applied simultaneously at both circuits. This way we can compare the two outputs directly, the one from the actual XOR gate and the one from the circuits that we say is working like an XOR gate. Right now you can see that both inputs are set to 0. As a result, the output of the circuit representing the XOR gate and the XOR gate itself are both at 0. Let's change now the B input to 1, leaving A set to 0. Now the output of the circuit is a 1, as well as the output of the single XOR gate, exactly like we expected. Now I am switching both inputs. Now A is at 1 and B is at 0. And you can see that the outputs are still both at 1, like in the truth table. Finally, let's set both inputs to 1. Look, the output this time is a 0. And so we have a 1 only if the two inputs are different, otherwise we have a 0. Let's now work on the XNOR gate. Here is its truth table. And since this is a NOT XOR, the outputs are exactly the inverse of the XOR gate. As such, when we refer to the symbol for the XNOR gate, we just draw the 1 for the XOR gate, and then we put a NOT at its output, this circle. Like with the OR gates, we have ICs that can provide multiple XNOR gates, like this one in the picture. In this case it provides 4 gates, each one with 2 inputs. Let's now repeat the previous exercise to draw the schematic for this gate. These are the rows that present A1 at their output. For the first row, since both A and B are at 0, we have to write not A and not B. Then we write the OR symbol, and then we add the part relative to the second row with an output of 1. In this case, both the inputs are at 1, and so we simply write down the names of the inputs. This boolean expression now represents the truth table for the XNOR, so we put it equal to U. To draw the schematic, we write first the names of the two inputs. Then, since we need both the direct and the inverse values, we add a NOT gate to both. The AND gate will have at its inputs both NOT A and NOT B. For the second part of the expression, we need a second AND gate, and this time, however, the inputs will be direct values A and B. Finally, we use an OR gate to combine together the two AND gates, as described in the Boolean expression, and the output of the OR gate is the output of our circuit. We can verify that this circuit satisfies the truth table by noticing that while one of the two AND gates takes A and B, the other one takes not A and not B. As a result, only if A and B are exactly the same, one of the two AND gates will output A1. Otherwise, if A and B are different, the AND gates will always have A0 and A1 as inputs, which will cause them to output A0, both of them. And so, in the case A and B are the same, the OR gate will receive A0 and A1 at the inputs, and therefore giving an output of 1. Instead, in the case where A and B are different, the OR gate will receive A0 on both inputs, therefore giving A0. Let's use again the simulator to prove that. Here is the simulator workbench with the XNOR circuit already drawn on it, as well as a separate XNOR port that we will use as a reference like we did before for the XOR gate. You can see right now that both inputs are set to 0, and the output of the circuit is at 1, as well as the one for the XNOR gate. and so the first row of the truth table is actually verified. Let's put now the second input at 1. Now both the outputs of the circuit and the output of the XNOR are giving us 0, and this verifies the second row of the truth table. Switching the two inputs, the outputs are still at 0, and that proves the third row of the table. And finally, a 1 on both the inputs generates a 1 on both outputs, which verifies the last row of the truth table. Whenever you have a truth table that describes a certain logic function, it is always possible to write the boolean expression equivalent to the truth table, and from that we can finally draw the schematic for such function. Isn't that really neat? And note also that if we have a truth table with more than 2 inputs, we can still go through the exact same procedure, just keep in mind that we will need gates with more than 2 inputs. Next time we will go through something like that, and I will show you that we can even do a step further and manipulate the boolean expression to be able to draw a schematic that contains just one kind of gates, rather than multiple. And this in fact simplifies a lot the assembly of logic circuits, because we can make them using over and over the same kind of IC rather than multiple different types. But this is a topic for another time. If you want to see that, come back to the future episodes of this series, and to make sure you don't miss any, just subscribe and enable the notifications, and so you will be informed whenever a new video becomes available. See you in the next video, and as usual, happy experiments!